This problem is from the text Conceptual Dynamics. In particular, we are going to perform an extension of the solved problem 3.2-9 from the textbook. In other words, we'll quickly go through the details of this solved problem, which you can find in the textbook entirely worked out, and then we're going to perform an extension of this problem. And so this problem states, a projectile is launched with an initial velocity of 100 meters per second at an angle of theta equals 45 degrees with respect to an inclined hill. If the hill makes an angle of phi equals 30 degrees with respect to the horizontal, how far down the hill d does the projectile land? So we read the problem, attempt to understand what's going on. We write down what's given. So we're told what the initial velocity of the projectile is. We're told the angle with which the projectile is launched, in particular with respect to an incline. And we're also told the angle that the incline makes. So this is phi. We are then asked to determine how far down the hill does the projectile land. We want to find this distance d. And so within the book, you can find the details of the solution of this problem. With projectile motion problems in general, we like to use a rectangular or Cartesian coordinate system. So we define an x-coordinate system, an x-coordinate axis that's horizontal, and a y-coordinate axis that's vertical. And the reason that we do that is because the acceleration due to gravity is entirely in the y direction, and if we neglect air resistance, then there's no acceleration in the x direction. And so the fact that we can consider the acceleration in the x and y completely separately allows us to treat this projectile motion problem as sort of two rectilinear problems. Following the details in the book, we determine that the solution for the distance traveled is equal to this equation, and for these particular values, it comes out to be 1,857 meters. We are now going to perform an extension of this problem. Specifically, we want to determine the angle that will cause the projectile to land the farthest distance down the hill. So we still have the same initial velocity, and we still have the same incline of the hill. But now we're not going to assume that theta is equal to 45 degrees. We want to determine the specific theta that gives us the maximum value of d. And so you can sort of imagine if we shot this projectile at a shallow angle, very close, barely above the incline, it may not give us a very large distance. And so if we increase the angle at which the projectile is launched, we maybe are able to get a farther distance. But if we make the initial angle too steep, it'll become smaller again. So intuitively, you can sort of imagine that there's some middle ground, some middle theta that will give us the maximum distance down the hill. Here again, we have our solution. This phi is just a constant 30 degrees. G is just a constant 9.81 meters per second squared. The x and y components of the velocity can be found via geometry. Specifically, if we look at the initial velocity, you can sort of imagine that we have a component of the velocity in the x direction and a component of the velocity in the y direction. So we have this right triangle where this angle is theta minus phi. So in this case, the initial x velocity is the velocity in the x direction for the entire time that the particle is traveling, because there's no resistance. Because there's no air resistance, therefore the acceleration in the x direction is 0. So we have that the x velocity is equal to the initial velocity times the cosine of the angle, because cosine gives us the adjacent side of the right triangle. where again this angle is theta minus phi. And then we have the initial y component of the velocity, and we find that using sine because the y component is the opposite side of the angle. And so if we look at this equation, we can substitute in for v sub x and v sub y 0. And we have d as a function of theta and a bunch of constants, but the only variable is theta. And so in essence, we want to find the value of theta that maximizes d. If you think back to calculus, one way that we can do this is by taking the derivative of this function d with respect to theta, with respect to the variable we want to find, and set it equal to 0. And that, in essence, means that considering a graph of d versus theta, we know at shallow angles, maybe we don't get very much distance. We increase the angle, we get more distance. But if we increase the launch angle too much, the distance traveled will start to decrease. So we want to find this maximum, and it's intuitive that the slope at the maximum is 0. And that is why we want to solve this equation, the derivative of d with respect to theta, and set it equal to 0. So we can definitely do that in this case. It's a little cumbersome. We have to use some chain rule, we have to use some product rule. When we finally get here, when we finish taking the derivative and we have this algebraic equation that we want to solve, that we want to find the roots for, it can be a little challenging. We may have to use a solver, we may have to use some trig identities, but it can definitely be done. The alternative is to sort of do this in a brute force way. We just start trying a bunch of different thetas and find the one that gives us the largest d. So in essence, we graph this function and pick off the maximum. And I'll refer to that as sort of solving this problem numerically. And that's something that I'll come back to throughout the course, but sometimes we have a problem or an equation that's difficult to solve analytically or difficult to solve by hand to get a closed form solution. And so we basically use computer software to do it for us. And so this is the approach that I'm going to take, and I'm going to do it in two ways. One, I'm going to use a computer language, in this case MATLAB, and then I'll repeat that using Excel. So in particular, I'm going to use a program called MATLAB, but this code is written in very much the same way that you would write in any sort of standard computer language. And so at the beginning of the program that I've written, I define the constants. So I define what the initial velocity is, or the initial speed. I define the incline of the hill, and I converted it into radians. So it's 30 degrees, but then I converted it into radians because the sine and cosine function we're going to use assumes an angle in radians. And then I define the acceleration due to gravity. So I can run that piece of the code. And then the next part of the code is basically a large for loop. And so I'm just going to calculate the distance traveled d for a bunch of different thetas, specifically as theta is varied from 1 degree to 120 degrees. So 1 degree is just barely above the incline, and an incline and a theta of 120 degrees works out to be straight up. So it's 120 degrees above the incline, but the incline itself is angled 30 degrees. So I'm going to vary the launch angle from just above the incline to straight up vertically. So I have a for loop. I have this index I, and I vary it from 1 to 120 in steps of 1 degree. And so I'll define theta, where this is the index. So, this will give me an array of thetas. with 120 elements. So the first element will be 1 degree, and then the next time through the loop it'll be 2 degrees, and the next time through the loop it'll be 3 degrees, and so forth. Then I define this angle alpha, which is how far the launch is above the horizontal. So I convert the theta into radians and subtract off the incline of the angle, the incline of the hill, to get how far the launch is above the horizontal. And I can calculate the x component of the velocity. I can calculate the y component of the initial velocity. And then I write my equation for d. So this is what we had in our PowerPoint slides. There is a function cosine defined in MATLAB. We do multiplication with the asterisk. We do division with the slash. We do an exponent with this caret, raise it to the second power. And then I end the for loop. So it basically loops through this 120 times, calculating the distance for all those different values of theta. And then the last part, I actually plot the graph of theta versus d and add some labels and titles to my graph. If your programming language doesn't have a sort of plotting capability, you can simply just look at the array, or there's sometimes a built-in function that'll find the maximum value of the array, things like that. So if I run it, this is the graph that I get. Along the x-axis is my launch angle in degrees. Along the vertical axis is the distance d down the incline. And if we look at this, it appears that we get our maximum distance of 2,039 meters at a launch angle of 60 degrees. If we actually, did the calculus and took the derivative, we would get the same answer. So now we'll go ahead and repeat this process using Excel. So here is an Excel spreadsheet. Over here I've defined some constants, the same sort of constants we defined in the MATLAB program, the initial velocity, the incline of the hill, and the acceleration due to gravity. Here I have a column for the angle theta, the launch angle, and we're going to calculate the distance traveled from 1 degree down to 120 degrees. So in this first cell, I just entered 1. In the second cell, I'm going to enter an equation, so I do an equal sign, and then I reference the cell right above it, which is cell B2. So this is column B, row 2, and I'm going to add 1 to it. So I'm going to calculate things for theta equals 1, theta equals 2, and then if I drag on this cell and pull it down, it's going to repeat that equation, but it's going to automatically update the value of that cell. So as I pull it down, so this cell now references B3, this references B4, this references B5, and I can pull it all the way down to 120 degrees. In the second column, I calculate alpha, the launch angle above the horizontal. So I take my theta, so I have my theta from cell B2, I convert it into radians. Within Excel, it has the variable pi. I reference it using this syntax. And then I subtract off the incline of the hill, which is over here in cell J4, column J, row 4. And I added this dollar sign to the J and to the 4 to keep those constant. So when I drag down this equation, I don't want to, I want my theta to change. I want this to update from B2 to B3 to B4, but I don't want the incline of the hill to change. It's a constant, and it's located in this cell, and so adding these dollar signs keeps that cell constant. So as I pull down, I can see that the B3 updated, but the J4 didn't, and so on. Then I calculate the x component of the velocity, which is the initial velocity, which is again a constant. I multiply it by the cosine of alpha, the distance above the horizontal. I can calculate the initial velocity in the y direction. Instead of using cosine, I use sine. So Excel understands or has a function for sine and cosine. It's assuming an argument in terms of radians. So that's why we did our angles in terms of radians. And then we have our equation for D, which again is the same equation from our PowerPoint slides. It's the same equation from the MATLAB program. It may be a little hard to follow, but if you sort of dig in there, you can do it. Uses the same symbols for multiplication, division, and exponents as we did in MATLAB. And again, if we just take all of these cells and drag them down, they will update as we change the value of theta. I want to drag it all the way down to an angle of about 120 degrees. So we can see how the distance has changes as we change theta. And then we can plot this. So I go ahead and highlight my x-axis, theta, hold down the control key, highlight the column that I want to use for my y-axis, the distance. And then up in the toolbar, I can insert a scatter plot. I will show it as lines that are sort of connecting the dots. And I get this graph, which is identical to what we found using MATLAB. So at shallow angles, we don't get much distance. We increase the launch angle, we get a farther distance, but if we increase the launch angle too much, the distance traveled starts to decrease. And our maximum is just above 2,000 meters at an angle of 60 degrees. We can change the title, we can add labels, we can change the location of the graph, but in essence, you see that it's the same result that we found using MATLAB. So that brings this example to a conclusion.